Now in our video for today, I will discuss about friction, and we will specifically tackle problems involving wedges. And so again, friction forces result from the roughness of our surfaces because it adds some resistance, and then we will be dealing with wedges. Now the shape of a wedge is usually triangular or trapezoidal if you look at the cross section, and then it is generally used for slight adjustments in the position of a body, like for tightening shifts or keys for shafts. And so now we have this problem. We have to determine the smallest force P needed to lift the 3,000 pound load, and then the coefficient of static friction between A and C and between B and D, or mu s, is 0.3. And then between A and B, mu s prime is equal to 0.4. And then for this problem, we are to neglect the weight of each wedge. Now, we still don't have our figure, and so it looks like this. This is our wedge. Now, as I mentioned earlier, wedges are usually trapezoidal or triangular in shape, and so these are both trapezoids. Now, this is our wedge A, and then this is our wedge B. And then this is point C, which describes the ground. And then this is point D, which describes our wall. And then this is our force P, which we are trying to solve. And then this is the 3,000 pound load that acts along this one. And so now, let's just redraw this one. And so we have this figure. Now, if we are solving friction problems, we have to simulate in our minds first what's going to happen to our objects. Now, if we are going to apply a force P here, acting to the right, then we know that wedge A will move to the right. Now, if wedge A will move to the right, then wedge B will naturally move up because this will fill in the space here. And so if we will simulate that movement, it will look like this. Let's apply the force P, and then let's move this one here. And so again, this is our original position. And then if we apply P, this will move here, and then wedge B will move up. And so now we will be able to determine the direction of friction because our frictional force always acts against the movement of the body. And then for this part right here, if we'll go back, we have different directions in our frictional forces because for this block, the movement is toward the right. And so to resist that one, we have a frictional force here and also here, considering this block. However, considering this one, we have a normal force here. And so if we have a normal force here, then something should oppose that one. And so for this block, our frictional force will act this way because the horizontal component of this one will counteract the normal force. And so that's essentially the direction of our frictional forces. And then for the ground, again, block A will move to the right. And so between the ground and the wedge A, we will have a frictional force resisting that movement. And so this will act to the left. And then for the wall at D, we know that this block will move up. And so our frictional force will resist that movement. And so it will act downward. And so now we can isolate these two bodies. And so let's just copy this one. And so again, we have this figure. And so let's first look at our figure externally. And then let's try to draw the frictional forces. Now again, if we apply a force P here, then this will move to the right. So our frictional force between the ground and the wedge at A will be acting to the left. So it will be this one. This is, let's say, the frictional force acting at C. And then this block will move up. And so our frictional force at D will resist that movement. And so let's label this one as FD. Now sir, what will be the value of the frictional force? That's where our coefficient of friction will come in. Now we have this one. Between A and C and between B and D, the coefficient of static friction is 0.3. And so we'll write that here. Between A and C and between B and D. So for this one, we have mu is equal to 0.3. And also for this one. And then between A and B, our coefficient of static friction is 0.4. And so that will be here. Let's zoom in. That will be right here. This is mu s, and also this one, and this is mu s prime. And then this is equal to 0.4. This is the coefficient of static friction between wedge A and wedge B. Now again, we have to isolate these two because the frictional force acting at A will not have the same direction as the frictional force acting at wedge B. So let's separate the two. Let's just move all of these. And so now our two wedges are already separated. Now again, between the wall and the wedge at B, we will have a normal reaction. Now let's call this ND. Again, this is point D. So I will just label this one as ND. Now our normal force will always act perpendicular to our body. And so that's why this is acting to the left. Now sir, why is this acting to the left. Now that's because we are applying a force P here that acts to the right. Something must resist that force. And so that's why we have a normal reaction at D. And so to maintain equilibrium, our frictional force at this junction should be acting to the right to oppose this force. Again, your frictional force is always parallel to your body. And so our frictional force will act this way. This is parallel to this one. Again, just to make it clear, if we are dealing with normal force, this is perpendicular. And then for frictional forces, it will act parallel to your body. And so you have to remember these. Now let's label this as, let's say FE. Again, let's go back to our figure. Let's just label this intersection as E. And so we have this here. Now this is also 15 degrees. Because this is sloping at 15 degrees. And so this will be 15 degrees. Now for this configuration, we have a frictional force here and a frictional force that counteracts this one. And so if FE here is acting downward and to the right, our FE here will act upward and to the left. And so this is FE. Now we are still missing something because we still have our normal reaction. Now this force acts downward, and then our frictional force also has a downward component, and also our frictional force here. And so to resist that one, we need to have a normal force right here. Now again, this normal force acts perpendicular to our body, and so essentially this is perpendicular to this line, and so that's why it has this orientation. Now let's label this one as NE. Now we know that we can get our frictional force using our normal force, because our frictional force is just the coefficient of friction multiplied by the normal force. And so essentially, Fe will be equal to mu times NE. Now again, our coefficient of friction at E is 0.4. And so let's write that here. This is mu s prime is equal to 0.4. And so our Fe will be mu times NE. Now our mu is 0.4. And so we can write this one as 0.4. So let's just change this one. We have Fe equal to 0.4 NE. And then we can also write Fd as 0.3 ND. Again, this is mu s times the normal force. And then we can change this one into 0.3. And so this will be 0.3. Again, for these two, this one and this one, we are just using this formula. And so now we can sum up forces vertical and horizontal to find our unknowns. However, we have two unknowns for this one. We have NE and ND. And so we will need two equations to solve the two unknowns. Now first, we can sum up forces vertical, considering this free body diagram. And so we have summation of forces vertical equal to 0. And so we have negative 3000 because it's acting downward. And then plus the vertical component of this one. Now this is the tricky part. What angle are we going to use? Will it be 15 degrees or 75 degrees? Now in order to visualize that one, let's draw some lines here. Let's zoom in. We will draw a point here. And then let's try to draw vertical and horizontal lines. And so this will be our vertical line. And then this is our horizontal line. Again, this normal force is perpendicular to our body. And so this angle is 90 degrees. Take note of this one. Now first, if you are to look at this triangle, this one, then this angle will be 90 minus 15, because this is a right angle, and then the sum of interior angles for triangles will amount to 180. And so to get this angle, we have 180 minus 15, and then minus 90, and then minus another value, which is, let's say, theta. So minus theta. We'll equate this one to 0. And so solving theta, we have 180 minus 15 minus 90 minus x. That's equal to 0. And so we have 75. And so this is 75 degrees. Theta will be 75 degrees. Now let's remove the triangle. Now again, this line and this line forms a 90-degree angle, because again, our normal force is perpendicular to the body. And so if this is 75 degrees, this one, then this must be 15 degrees. So that 75 plus 15 will amount to 90. And so I will just erase this one. And then let's try to write what we have established. Now, this is 15 degrees from our calculation. And so we will be using this angle. Now, if you want this one with respect to the horizontal, then you may get this one, because this angle is also 90 degrees. And so this will be 75 with respect to the horizontal. However, I will just use this one with respect to the vertical. Now, to get the vertical component of NE, we have to use the cosine function. Now sir, why not sine? We are not using sine because our angle is with respect to the vertical. And so if we will try to redraw this one, we have NE, and then let's draw a vertical line. Now this is 15 degrees, and then let's say this is our horizontal component and this is our vertical component. And so if we will extend this one, this will be the side opposite to our angle. And so we will use sine for this one, because again, sine theta defines opposite over the hypotenuse. And so our opposite side will be the hypotenuse times sine theta. It will be this one. Now our hypotenuse is the normal force at E. And so let's change H into NE. So this will be NE sine theta. And then using the cosine function, we have this one. Cosine theta is equal to adjacent over hypotenuse. Now this is our adjacent side, or this one. And so our adjacent side will be H cos theta. Again, H is NE, and so this side is NE cosine theta. Now I hope this is clear. Now going back, we are summing up forces vertical, and so we have NE cosine theta. So NE cosine of 15 degrees, because that's our angle. So this is 15 degrees. And then this is plus because this is acting upward. And then we also have 0.3 ND, which is acting downward. So that will be minus. We have minus 0.3 ND. However, we are still missing something, because this frictional force also has a downward component, and so we will need to get that one. Now in order to get the component of this one, we need to make this as our hypotenuse, and so we can draw a line here. Let's extend a horizontal line, and then this will act to the right, and then let's draw a downward line. So this will act downward. Now this angle is 15 degrees because this is with respect to the horizontal, and then this is also with respect to the horizontal. So this is 15 degrees. Now I'll just use another color. This is 15 degrees. And so let's try to zoom into this triangle. Now redrawing that one, we have 0.4 NE, and then we will draw this line. This is the horizontal component, and then this is the vertical component. Now again, this is 15 degrees, and so this component will be 0.4 NE, and then cosine of 15, because this is the adjacent side. And then for the vertical component, we have 0.4 NE, or again the hypotenuse, and then multiplied by sine 15, because this is the opposite side to our angle. And so we will subtract here this vertical component, which is 0.4 NE sine 15. And so now we will equate this one to 0. However, we need to first simplify this one to speed up our calculations. Now we can join this one and also this one because it has a common term NE. And so let's try to do that. Plugging in the coefficients, we have cosine 15 for this one, and then minus 0.4 sine 15. So minus 0.4 sine 15. And so we have this expression. Now instead of writing this whole expression, I will just store this into a variable. Now let's say I will store that at A. Again, that value is stored at A. And so if I will type A, it will give me that exact value. And so that's what I'm essentially doing here. And so we can simplify this one into A times NE. Again, this is the stored value, and then minus 0.3 ND, and then this is equal to 3000 if we will move this one to the right. So this is 3000. Now sir, why are you moving this one to the right? I am moving that one to the right so that I can apply the two equations to unknowns calculator technique. And so this will be our first equation. Now sir, where are we going to obtain our second equation? Our second equation can be obtained by summing up forces horizontal. And so let's try to do that. Summing up forces along x equal to 0. Now again, for this free body diagram, we have ND, which acts to the left. And so that will be minus. So minus ND, and then plus the horizontal component of this one. Now this will be NE sine theta. So plus NE, and then sine 15, because this is our angle. And then for the last one, we have this horizontal component, which also acts to the right. And so that will be plus 0.4 NE, and then cosine 15. And then we will set this to 0. Now let's just move this one because we are running out of space, and also this one. Now we can simplify this equation further. We can join the coefficients of NE. And so we will have sine 15, and then plus 0.4 cos 15. That will give us 0.645. However, to use the exact value, I will just store this one into a variable. And so let's say I will store that at B. And so this will be the coefficient of NE. So I will store this one again at B. And so now our equation will be B times NE, and then minus ND. And then this is equal to 0. Again, this is the stored value. And so now I already have my two equations, two unknowns. And so to solve NE and ND simultaneously, I will just use my calculator. Now first, we have to go to mode, and then press 5 for equation, and then let's go to simultaneous equation, which is 1. And so we will press 1. Now let's first define that our first unknown x is an e, because it's the first expression in our two equations. And so let's say this is x, and also this one. And then nd will be our y. So this is y, and also this one. Let's make that clear. And so for a, I will type the coefficient of x. So I have a, which is the stored value. And then for b, I have negative 0.3, which is the coefficient of nd. So minus 0.3. And then that's equal to 3000. So this is 3000. And then for the second equation, the coefficient of ne is stored at b. And so I will type b and then press equals. And then for nd, my coefficient is just essentially 1. Now be careful of this one, because some students will write this one as 0. However, this is essentially negative 1. So minus 1. And then this will be equal to 0. And so to get ne and nd, press equals. The first value will be our ne, because it corresponds to our x. So ne will be 4485.37. And then this is pounds. And then our nd will be 2893.91. And so we will write that here. And so these are our two values. However, this is not what we are looking for. We are essentially looking for p. Now to get p, we need the equilibrium equations for this free body diagram. And so let's do that. Now again, Fe is equal to 0.4 Ne. And so this will be 0.4 Ne. Now since we already have Ne, we can solve this one. Fe will be 0.4 and then times 4485.37. And so we have 1794.148, or let's say 0.15. And so this will become 1794.148. And then the components of this one will just resemble this one. However, it will be acting opposite to this one. And so let's copy this one. And then let's try to change our directions. Now this is because our Fe will act toward this direction. And so let's change this one. It will act right here. And then this one will act toward the left. And then this one will act upward. And so we already have these. Again, this is just 0.4 Ne, which is this one. Now we also forgot Ne. Because again, if we have Ne acting here, then we must also have Ne acting here. Now that's to maintain equilibrium at E, or at this point. And so we have Ne. Now our Ne will also just use this angle. And so let's copy this one. However, what's going to change is the direction. Because this will already act toward here. And so our components will also change. This will act downward, and then this will act to the left. And so we have these components. And so now, I can sum up forces vertical and horizontal. And so summing up forces vertical, I have this horizontal component, which is Ne cos theta. Now Ne is 4485.37. And since this is acting downward, we will use minus. So minus Ne, which is 4485.37, and then cosine theta. And then our theta is 15 degrees. So let's change this one. And then I also have this vertical component, which acts upward. And so that will be plus 0.4 Ne sine 15. Now 0.4 Ne is 1794.148. And so I will write that here, 1794.148. And then sine 15. Now we are still missing something because we have a frictional force here, but we did not write our normal force. This is supposed to have a normal force at C. And then Fc will be mu times N. Now our mu is 0.3. So this is 0.3 times the normal force at C. So this is NC. And so I will still add here NC. Let's write that one. And so I will set this one to 0. And so now I can get NC because it's the only unknown. And so solving that one, I can just move this to the right. That will become positive. And so 4485.37 cos 15. And then minus 1794.148 sine 15. And so that will give me 3868.18. So NC is equal to 3868.18. And then this is pounds. And then to get P, I will just sum up forces horizontal. And so summing up forces horizontal, I have P, which is acting to the right, so positive. And then minus this horizontal component, which is Ne sine theta, so 4485.37 sine 15, and then minus this horizontal component. So that will be minus 0.4 Ne is 1794.148. So 1794.148, and then cosine 15. And then I also have 0.3 NC, which is acting to the left. And so that will also be minus. So minus FC, which is 0.3 times NC, which is this value. So 3868.18. And then I will set this one to 0. And so I will just move these expressions to the right. And so I will have positive 4485.37 and then sine 15 plus 1794.148 cos 15 and then minus 0.3 times 3868.18. I mean plus. Because we are changing the sign. And so that will give me 4054.37. And so P will be 4054.37. And then this is pounds. And so this will be our final answer. Because again, we need the smallest force P that's needed in our figure. And so let's just copy this one and then let's place it here. Now this is our requirement and this is our answer.